So we are very happy to have Christophe Garban from Lyon, which is in France, who will tell us about his exciting work with Thomas Spencer and Avelius Sepulveda. And I'm very happy to give Christophe this medal, which the Congress gives to every speaker. So it's yours.
Okay, so thank you very much for the invitation. So I will tell you about a joint work with Tom Spencer, and in the second part about a joint work with Avelius Sepulveda. And both of these works will be related somehow to Bayesian statistics. So I will start the talk with an illustrative picture of what those Bayesian statistics will be. And there will be two kinds of Bayesian statistics. Each of these in this illustration have to do with the most famous monument of Geneva. So in the first part with a... okay, so I've been told it was tricky to use. Okay, so in the first part with Tom Spencer, the Bayesian statistics will start with an object, and we will add noise to this object. And the purpose of Bayesian statistics often is to try to recover what was the initial image or object given the noise data. In the second part of the talk, which I think will be short because of time constraints, in the second part of the talk, okay, so maybe I should forget about the pointer. So in the second part of the talk, we'll be given an object, and we will not add noise to it, but instead we will be given a very partial information, and the goal will be to try to recover the initial object. Okay, so this first slide is a quick reminder about what spin systems are on ZD. So there is a grid, ZD on the top. And to each vertex of this grid, to each site x in ZD, we assign a spin that I will usually denote by sigma x. And in the most famous case, this spin lives in a plus minus 1. It's called the Ising model. And it comes with an Hamiltonian, which is in blue here, which is exponential beta, sum over the nearest neighbor edges of sigma I times sigma j. The second model is called the XY model, and now the spins, they live in the unit circle S1. And the Hamiltonian has the same form. It could be written sum over the nearest neighbor of sigma I scalar sigma j, but here I'll write it as a sum of cosine theta I minus theta j, where theta I is the angle of the spin at site I. The third model is called the classical Eisenberg model. So we've heard several times about the quantum spin model in this conference. Here it's the classical case. Spins take their values in the unit sphere S2, and the Hamiltonian again is the same thing. And the last model, which is maybe slightly less standard, to each point in ZD we assign a group element that I will denote by U of x. And the Hamiltonian is a little bit like a sum of a cosine between I and j, but here I have to take ui star times uj, where ui lives in some Lie group, for example, SU2. And to turn it into a proper Gibbs measure, I take the trace of this matrix and then the real part if it happens to be complex matrices. So this gives me several spin models on ZD. And it's well known in the first case, in the case of Ising model, that there is long-range order as soon as the dimension d is greater or equal to 2. And this goes back to Peierls. I will give very, very few references along the talk, really the very first ones each time. For the second, third, and fourth model, it is known that there is no long-range order in dimension 2. So for the second one, the case where the spins are in the S1 unit circle, there is a fascinating to me phase transition, which is the BKT transition, and which has been proved by Fröhlich and Spencer in 81, and I will maybe go back to this in the second part of the talk. But this first part of the talk is about long-range order, and by Mermin-Wegner argument, there is no long-range order for this continuous spin system in dimension 2. Long-range order only starts in dimension 3. And for the XY case, there are several possible proofs for the long-range order, but for the Eisenberg and the non-abelian group-valued spin systems, there are much less available proofs. And this will be the next slide. So when the symmetry group starts being non-abelian, the most famous tool to analyze those systems is called the reflection positivity. And it goes back to a famous work by Fröhlich, Simon, and Spencer in the late 70s. And so they could identify long-range order at low temperature for those systems, but there are many constraints. There are geometric constraints. The domain needs to have lots of symmetries. You need to be able to apply lots of reflection with respect to hyperplanes, and basically you have to work on the torus. And also those proofs, they only give information about the average two-point correlation functions, even though there is a recent work by Lis and Taggi which improves on this. And there is also another work which is probably more flexible but is also very hard, which is a series of work by Balaban in the 90s. But besides these two techniques, there are no ways to attack long-range order for those systems. And of course, Peierls type of arguments are impossible because of the continuous symmetry. Okay, so the purpose of this talk will be to give a third way to detect long-range order for, in particular, non-abelian spin systems in dimension d greater than 3. It will have its own advantages, also its own restrictions. And one advantage, which will also be a restriction, will be that it will hold for disordered models. So in this slide, I want to start defining the type of quench disorder that we will consider in the simplest case of the XY model. There are several types of quench disorders you could think of in the magnetic direction. Here it will be in terms of the coupling constants. So the quench disorder will have a very simple probabilistic structure. It will be given by random coupling constants Jij, which are simpled independently on each edge of ZD. And to make the model simple, think of these as coin flips that will be 1 with probability P, minus 1 with probability 1 minus P. And so in particular, if P is very close to 1, if P is equal to 1, say, or very close to 1, most edges, most coupling constants will be equal to 1. So your model will be basically, this Gibbs measure, which is a random Gibbs measure, will be basically the same as the one I defined before. In other words, there will be very few frustrations, and the model should look like the normalizing model. And when P gets smaller, you introduce more and more frustrations into the systems. The red edges are the edges where J is equal to minus 1. And so the model should look more like something like a spin glass. And now you have an interesting phase diagram. There are two parameters. Here there is the temperature on the vertical axis, and there is this p-value, which represents the amount of disorder. And so this axis here is the classical Ising model. So it's known that there is a critical temperature. In dimension 2, this would be the Onsager temperature. And now you can think of what's going on in the plane of these two parameters. And the picture is from a paper by Nichimori in 1981. And let me start with a result that arises slightly after. Origoshi and Morita, they proved that in this part of the plane, when P is close to 1 and when the temperature is small, you do have long-range order. So that's probably intuitive because P is close to 1, so you have few frustrations. Temperature is very low, so in the Ising case, you can still run a Peierls argument and deal with this disorder. So with nowadays techniques, this would not be too hard to implement a Peierls argument and open this and prove this open region here, green. A more interesting aspect for the talk today is the discovery by Nichimori in 1981 of a spatial line, which is this dotted line here. And along this spatial line, Nichimori discovered that there are some thermodynamic quantities that can be computed exactly. And so this is a beautiful discovery, and this Nichimori line will be a key aspect of this talk. Okay, so the second model that I want to define before going to the G-valued case is the certain disordered XY model. And also here, I will attach ID random variables on each edge of ZD. And now the variables are not plus or minus 1. There will be angles, random angles, that will introduce some disorder. And there will be variables with values in minus pi, pi. So now there is more variety, more possible laws than just coin flips. And the type of probability measures that we will consider on the circle or on minus pi, pi are these rho u measures. So it's a measure on minus pi, pi that I represented on the pictures on the right. And remember that when the parameter u will be very small, it will be the same as p being small in the slide before. In other words, the random angle that you put on an edge is going to be more or less the uniform measure on the circle or the uniform measure on minus pi, pi. And because of this, it will introduce many frustration, a lot of disorder along the edges here. On the other hand, when u goes to infinity, it's going to be more and more centered around the zero value, the zero angle. And basically, you will not introduce any disorder in your system. This will be almost like a classical XY model. So now I mimicked the diagram by Nichimori in 81, and there is this parameter, which is still p. I wrote it as 1 minus exponential minus u, like in FK. And there is this parameter in temperature here. So when u is infinity, when p is equal 1, this is the classical XY model. And in dimension d greater than 3, there is a critical point. And there is long-range order at low temperature with, as I said before, several different proofs. So now there is a natural question, which is if you look into the plane P and T, or the plane U and T, what is going on with the long-range order properties here? The Morita result that I defined earlier the proof cannot hold anymore because you cannot run a pairs argument in this little part of the plane because of the continuous symmetry of the spin systems. So I think so far it's not known what's going on here. But on the other hand, there is this line, this Nichimori line, that also works in the case of the classical XY model. And Nichimori, in fact, discussed this Nichimori line for the disordered XY model in early 2000. And this Nichimori line, in this way of parameterizing things, corresponds to plugging exactly u equals beta. So in this distribution, I want to have u is the same thing as the inverse temperature. And the last model I want to discuss before giving you a result is the disordered Lie group valued models. So I still have on each vertex of my graph here spins that takes their values in G. And the disorder now will again be an ID field that will live on the edges of the graph, and it will be made of ID now matrices. They're not just angles anymore. And these matrices, I will call these omega ij, and they will be distributed according to a generalization of what I just said before. So it's some measure on the group, which has a Radon-Nikodym derivative with respect to the R measure on the group. And it still has the property that when u is very small, it's more or less the R measure. It's very disordered, many frustrations. And when u is large, this measure is more or less concentrated around the identity of the Lie group G. So we still have this diagram here. And on this axis, we have the classical G-valued spin model on ZD. And reflection positivity works very well there. And you have long-range order up to a certain point, which is not quite the true critical point. And this is well known since the late 70s. Now you can also define a Nichimori line, which corresponds to this u equals beta. And as in Nichimori works, it's easy to see that you can compute exactly some thermodynamic quantities. So I hope at least these disordered models are clear. Let me just emphasize that when you are at beta very large, you are very close to the classical spin models here. The curve is very near the classical case because the disorder is almost flat. So now let me state the result we showed with Tom Spencer. So what we show, we do not have this Morita and its co-author result on an open neighborhood here. But what we can show is that there is long-range order for these non-abelian spin systems along the Nichimori line for a certain while. And the interest of the result, I think, is twofold. So first, we do have long-range order when there is a little bit of quench disorder. But maybe the main interest of the proof is that the proof is quite simple, at least much more simple than Balaban, for sure, and is much less restrictive in certain ways than proofs using reflection positivity. And I should stress that the proof is highly motivated. It's inspired, it's based, and it was even somehow suggested in a work in Bayesian statistics by these authors, Abe, Massoulier, Montanari, Sly, and Srivastava. And you can see from these authors that they are not completely uncorrelated from statistical physics. And based on their works in Bayesian statistics that I will tell you about in the next slide, we prove this long-range order property that when beta is large enough, at low enough temperature, the average quenched two-point correlation function does not degenerate as x and y goes to infinity. And one nice aspect of the proof is that we don't need to work on the torus or anything. We could consider long-range models. The graph could have holes. The coupling constants don't have to be equal everywhere. So it's not restrictive in that sense. The restrictive part is that we must be on this Nichimori line. Otherwise, at the moment, the proof cannot be generalized. Okay, so I also emphasize that the result holds for the quenched model. So with high probability in omega, you have long-range order at far distances. So now in the, I'm going slower than I wanted, but in the remaining time in this part one of the talk, I want to tell you a little bit about Bayesian statistics, about this work by Abe et al. So here you're on the grid. It's called group synchronization. You're on a grid ZD. And on each vertex of ZD, you have a certain group element that I denote by G of x and not U of x, because I want to think of this as a fixed initial data. There is no Gibbs measure or anything. You have group elements everywhere. You could think of it as cameras in Z3 that are pointing in some directions, represented by SO3. And the statistical problem you want to solve is the following. You're given the following data. For any nearest neighbor edge, like this ij here, you're given the increment in the group, gi minus 1 j of j, but there is some noise that has been added to it. So you have a big data made of all the group increments from a site to its neighbor, but it has been noised. And the question you want to solve is, given this data, so I will call y ij the noised increments on all the edges. Given that noise data, can you recover the increments from a point x to a distant point y? So it's a very well-defined statistical question. And they managed to answer this question. So let me first tell you what you would do if there was no noise. So this is very easy. If the data is noiseless, then to recover gx minus 1 gy, you just take one pass, and you multiply the group increments along that path, and by definition, this will give you what you're looking for. But now, if you start having noise in the system, if you take one path and you integrate, you multiply along that path the group increments, you'll accumulate a lot of noise along the way, and as you will reach from x to y the point y, if y is really far, you will basically have a uniformly chosen point on the Lie group, and it will not tell you anything. Nevertheless, using just one pass, let me tell you how to define an estimator. So I used statistical notations here with a wide hat. So I want to estimate this increment given the noisy data. And my first attempt is to multiply, as I said, the group increments. So a first caveat for this estimator is that if you average this estimator with respect to the noise, as I said, it's almost the R measure, so it will give you almost 0, and it will not give you much information. So the first step is to boost, to renormalize this estimator so that at least its expectation value here will be centered around your goal, around what you want to recover given the noisy data. So I passed the detail, but you need to renormalize by something which is multiplicative which is exponential in the length of the path. And the second thing you need to do, once you have a good estimator here, which is centered around the goal, you still have an issue, which is a classical issue in statistics. The variance is going to blow up. And the variance will blow up because you will accumulate too much randomness along one given path gamma. So the idea that they had was to average over as many paths as possible that go from X to Y. And the very interesting, so the variance is given in a rather simple way given a random measure on path. It's going to be these kind of exponential moments on the intersection between two randomly chosen paths gamma 1 and gamma 2. And at this step, I think there is one very interesting probabilistic input, which is from Benjamini, Pimentel, and Perez. I think for us probabilists, if we were to start from this observation, we would naturally consider the uniform measure over all the paths that go from X to Y. If you do this in dimension 4, this will work. It will give you a good statistical reconstruction algorithm. But in dimension 3, it makes these moments blow up. So probably, at least myself, I would have stopped here, I guess. But at the time, for different motivations, Benjamini, Pimentel, Perez, they managed to build a different kind of measure on paths going from X to Y, which have the property that these exponential moments are actually finite. And the interesting thing is that this exponential moment has a finite radius of convergence, so there is really a phase transition hidden in this property here. Okay, so I'll just quickly finish part 1, and I know very few times for part 2. So in 2 words, the proof combines these deep ingredients from Abe, Masoulier, Montanari, Sly, and Srivastava. And it combines another ingredient which is deeply inspired from the work of Nichimori, which is in more probabilistic language, the following. We show that there is exact independence of the increments under the appropriate measure, which here would be the average quenched measure, which is a different thing from the annealed measure. So under the average quenched measure, group increments exactly decorrelate along that line, and combined with this reconstruction operator from Abe, Masoulier, etc., we do get the long-range order property. Before giving some remarks on the part 1, I want very quickly to stress that in a subsequent work, we want to generalize this to abelian lattice gauge theory, which is supposed to represent QED and not QCD, as we had a talk yesterday by Ilya. And here, so it's abelian lattice gauge theory. There is an action which is a little bit like the XY action. And similarly as in the XY, one can consider some quench disorder here. And there is also a Nichimori line for this abelian lattice gauge theory. And just in one slide, I can tell you the theorem, which is extrapolating the confining-deconfining transition that was proved by Gutt in 80 and Fröhlich-Spencer in 82 to this quench disorder setting, where there is a deconfining phase at low temperature and a confining phase at high temperature. And just in one word, the proof now requires to average over surfaces that are on this Wilson loop observable. So I'm going a bit too fast here, but very quickly some comments. So I was very vague about boundary conditions. We can handle both free and Dirichlet boundary conditions. But just to show you that there are also some restrictions, we cannot handle Dobrushin boundary conditions, for example. And to show that it makes things more flexible than reflection positivity, we can prove long-range order on 2 plus epsilon dimensional spaces using extensions of this Benjamini, Pimentel, Perez works by Hagström, Mossel, and Hoffman. Another comment is that I gave you a result for Lie group valued models. One can also build Nichimori line in the case of the classical Eisenberg model, but there are some further difficulties due to the fact that we don't quite have the nice group structure that we have with those Lie groups. And the last question that I added is because there were many talks that I've heard so far about quantum spin systems in this conference, and there is a natural question to wonder whether there is a Nichimori line and whether maybe one can prove a long-range order for the ferromagnetic quantum Eisenberg model with this setting, and I don't have the answer. How much? 1. Very good. So in the 1 minute left, I wanted to tell you a little bit about a joint work I did with Avelio Sepulveda, where it's another piece of Bayesian statistics where there is no noise added. And I will really try to make it just 1 minute, and I will use this similar trick as the trick Roland used on Tuesday, which is to point you towards a recorded video, if you wish, of last year. And in 1 minute, the goal was to try to extract nice geometric curves out of XY, or maybe more feasible villain model in dimension 2. And what we did is we postulated this conjecture by Fröhlich-Spencer in '83, which claims that the villain field in dimension 2 at large scale, seen as a complex field, should behave like the complex exponential of the Gaussian free field. And the question we ask is, given the complex exponential of the Gaussian free field, can you recover the Gaussian free field itself? And it's really like the picture I've shown here. You're given a partial information on the Gaussian free field. OK, I don't manage to. You're given a partial information, and you want to recover the whole field itself. And we could answer the problem as follows, that there is a nice phase transition for this statistical reconstruction problem. At low temperature, you can reconstruct, and at high temperature, by generalizing the delocalization result of Fröhlich and Spencer, it's just impossible to build a statistical estimator for it. So I will end here. Thank you. I'm happy to take questions if there are. Oh, OK.
OK. Questions? Yes?
Could you comment, please? It's here. Could you comment, please, on this difference between dimension 3 and 4 you mentioned for the Bayesian problem? You said that the naive strategy is supposed to work in dimension 4 and not in dimension 3. So could you comment on this difference? Where does it come from? And also, if possible, on what's the choice for dimension 3? How do they choose the path?
OK, so the point I wanted to make here was that if you do this group synchronization problem in Z4, so you have these group elements attached to the vertices of Z4, and you want to reconstruct Gx minus 1 Gy. If you do consider the uniform measure over the directed paths that go from X to Y in Z4, and you compute the variance of your statistical estimator, it will turn out to remain finite as X and Y goes to infinity, at least if the noise is not too large. So in that sense, the random walks, if you wish, they're good enough to solve this problem. But now if you go to dimension 3, if you do like a uniformly chosen directed paths that go from X to Y in dimension 3, there is less space. They tend to intersect more than they do in dimension 4. And in fact, it can be shown that there is no exponential moments for this problem. It blows up. And so that doesn't work. And so what you can do, so it was not quite the motivation of Benjamin Pimentel-Perez at the time, is to look for another measure which would have the property that paths do not like to sit too long next to each other. And that's what they built at the time. And they called those unpredictable paths. And the first measure they built was in dimension 1, to try to define type of random walks that avoid each other more than a simple random walk would do. And the second question I forgot, but
you answered both, I think.
Okay.
Yeah. Thank you.
So can you comment on this confining the confining transition in the four-dimensional gauge theory model? So in that case, you need abelian symmetry. You said there is no hope to get
yes, very good
non-abelian groups.
Yeah, so very good comment. So indeed, so in this theorem here, I'm stating the theorem only for abelian lattice gauge theory, while the theorem before did hold for non-abelian cases. So the big difference, which is interesting in itself, is that when you have spin systems, the correlation from x to y can be expressed as a product of those group elements along gamma. If you go to lattice gauge theory and you're interested in these Wilson observables that are here, if your gauge group is non-abelian, it is not true that you can express this Wilson observable as a product of a surface, of the plaquettes on the surface on this gamma loop. So you don't have this analog that you do with the spin system that you can integrate over a path. Here you cannot go to the surfaces, and it's only in the abelian case that you can still express things with surfaces, which are the generalization of those paths. And it's for good reasons, because if we were to prove this in the non-abelian case, it would prove with the same technique that you would have a deconfining phase for those non-abelian gauge groups, and this is conjectured not to hold. So there is a very good reasons why no hope to go to non-abelian case with this technique. Okay.
Can I have a question from online? Hello? I have a question from online. Roland Bauerschmidt asks, so he congratulates to a nice talk and then asks, does the argument give information about the truncated correlation along the Nichimori line? And either way, what is believed to be for the Heisenberg potential or exponential? Or exponential, sorry.
Okay, yeah, I think I got the question. So maybe you are asking, so the truncated correlation function, we also get those because there is a invariance under the G group. So when x goes to y at far distances, okay, so I lost my pointer here. But in short, it's easy to show at high temperature with a high temperature expansion that there is exponential decay of correlation. And so for the truncated correlation function, that solves what you're asking, because the average value, the 1-point function is 0, if you wish. And so the truncated correlation function is the same as the 2-point function. And it's also the case at low temperature if you take, for example, the free boundary conditions. But I'm not sure I answered you asked also about the Eisenberg model, right? Maybe.
No, he asks for what's the conjecture. So polynomial or exponential decay.
The conjecture for what? Sorry.
For the Heisenberg model.
For the Eisenberg model, the conjecture for the Eisenberg model, is that right?
Yeah, that was the question.
So for the Eisenberg model, I can even state a theorem, which is the same thing as I stated here. Where was my theorem? Yes. So for the Eisenberg model, we can build Nichimori lines as this one, but they do have a defect. They are less isotropic than this one in a certain sense. So when you go to the Eisenberg model, there are certain directions that need to be fixed, but there is still such a theorem with a quench disorder. I'm not sure I answer the exact question, but.
I think it's okay. Roland doesn't seem to complain.
Oh, it was Roland. Okay. Okay.
Yeah, it was.
Sorry, Roland. We can email.
There was another technical remark, but I think that's more for the organizer that about the participant panel in Zoom. But I think that doesn't go to you. Sorry.
What's the remark? I didn't hear.
Oh, this was a technical remark about the way the Zoom displays things. I think you cannot address that there. I think that's for the organizers.
You don't mean me. You don't mean them. Okay. Okay. Okay, so let's thank Christophe again. And our next talk is online. It's Massimo Gubinelli. Massimo, can you share your screen?
Yes. So do you hear me? Is okay?
Yes, we hear you fine.
Okay, so let me share my screen if I find it. Where it is? Yeah, here. Good.
I don't need.
Is okay?
Yes, you see that perfectly.
Okay. Yeah, perfect. Good.
Okay, so we are very happy to have Massimo. You can start.
Okay, thanks a lot. So I'm very happy also to be virtually there. Let me know if the sound is okay. I think I have a bad echo in this room, but anyway, it was the only room I could find. So the plan of, so I will not, the plan for this talk, it's not just to give you a precise result, at least I want just to discuss with you this general topic of stochastic quantization, and I mean, give you my impression of what this field is going and how does it look like and where I hope is going to, okay? And I welcome question and yeah, it was not my point to give a precise result, but really the general feeling of what is this direction of research, to me at least, okay? I don't think I can speak for many people. So this is my personal point of view. So the outline is as follows. So I want just to remind you what is an Euclidean quantum field briefly, and then what is stochastic quantization. I assume that many of you maybe ever heard of it, but my feeling is that somehow when I try to answer the question from people, they don't ask the right question from my point of view, okay? So I won't try to make what is interesting to me in this field. And then there are many ways you can do stochastic quantization, so I just want to introduce briefly them. And then somehow try to convey what is the information, new kind of information that stochastic quantization delivered with respect to other kind of techniques. And then also what are the open problem and interesting direction from my point of view, okay? So let's start. So Euclidean quantum field. So in this talk, without pretense of generality, so Euclidean quantum field, it's to me this very vague thing that is a measure on the space of distribution in the D-dimensional Euclidean space, which we describe very informally as to be the path integral with respect to this action. Okay, this is how it's motivated. If I have to go faster, that's essentially the motivation. But of course, all this is very informal. To me, would be even interesting intellectually to get a rigorous definition of what is a quantum field theory more precisely. But okay, that's I don't have right now yeah, I have various ways, but let's say that for this talk, this suffice. So I want to construct a measure which looks like this in the full space. And so the action, so it's like a Gibbs measure with this kind of action on path space. And the paths are actually distribution. So you start to understand that there are many problems with this expression. First of all, it's an integral in the full space. So it will not converge. It's an integral of things, of polynomials of a distribution, so it does not exist. And I resume here the problems, okay? So you have a large scale problem because essentially this measure cannot be defined in this way on the full space, cannot be defined in this way on the small scale because somehow anyway, you don't have this measure. And even if you try to make sense, you will encounter problems. So that's the problem of definition of Euclidean quantum field, how you get rid of this problem. The way usually you do this, you regularize the large scale and the small scale, and then you try to take limits and you have to renormalize. Okay, I will actually not even discuss in detail because it's the big picture which interests me. So you have to deal with these two problems. In the limit, maybe the measure is not even absolutely continuous with the reference Gaussian measure. So you have the problem how you handle this limit. And you see the interaction can be for various reasons, essentially only a polynomial, or in 2 dimension you're more lucky, you can take exponential or trigonometric function or linear combination of these things, okay? But let's skip this detail. You're welcome to ask questions if you really feel puzzled about this, okay? So the idea is that why these measures are interesting? Well, probabilistically they are a natural object, but they have an intrinsic meaning because essentially these measures are the only kind of candidates which have certain kind of property, which are these Osterwalder-Schrader axioms. They satisfy these axioms. And essentially they are the only object we know that we know to build that satisfy this axiom. And with this kind of object satisfying certain kind of axiom, then you can run a machinery which give you an Hilbert space, operators, and which satisfy relativity, special relativity. Okay, so this will give you a quantum field theory in the sense of like the marriage of quantum mechanics and special relativity, a theory which satisfy both constraints. Okay, so stochastic quantization. What is stochastic quantization? Is a technique introduced in the 80s by Paris and Wu to quantize a theory, so to construct this measure, okay? And so the idea is you want to build a measure new. In the previous slide, as the invariant law of stochastic partial differential equation, which looks like this, okay? It's essentially the PDE of parabolic kind. This was the initial idea of Paris and Wu. I will comment later on why it's so. And then you need to add a noise, so it's a stochastic PDE, and the noise is space-time white noise. And then I think a key point for me in this talk is that you have to introduce an additional parameter. So somehow instead of just looking at a function of the Euclidean space, you have to introduce a fictitious time, which you can imagine as a simulation time of a Monte Carlo Markov chain method. Okay, so it has no physical meaning, and actually you're not interested in this evolution. You just want to look at the result of the evolution at a given time, and essentially the Euclidean field has to be the invariant law of this evolution, okay? Why is this a good idea? So my point in this talk is that this is a good idea. So for Paris and Wu, they introduced for a deep reason. They wanted to quantize gauge theories, and gauge theories are notoriously difficult to quantize, even if you are a physicist. And for mathematician is an open problem, as we heard from, like, for example, Chevyrev talk, okay? And yeah, so the main point in my talk is that to me, stochastic quantization is a way to introduce a stochastic analysis of Euclidean quantum field. Okay, and the key point is that you have a new player, which is this Gaussian field here, okay, which does not appear in the previous problem. Okay, in this problem, you have a measure. Arbitrarily, you can decompose in 2 parts, but somehow here, canonically, you have this white noise, which is a non-perturbative object in some sense. And okay, so let's go back. Maybe I don't assume you are familiar with this language, and actually there is no definition, but of course there exists a field which is called stochastic analysis. And if you try to understand, okay, what is really stochastic analysis? When I teach to the students stochastic analysis, I teach Ito calculus. And Ito calculus was born for a very specific reason historically. And the reason of Ito to introduce Ito calculus was because he wanted to be able to construct diffusion process, so Markov process with continuous sample path. So this was his goal, and Ito calculus was his tool to achieve his goal. Okay, that's very clear from if you look at the history of this field. And so what is a Markov process? Well, a Markov process is just a family let's say, if you don't look at the path space, you start historically, it's just this family of kernels which satisfy Chapman-Kolmogorov equation. Okay, so it's a coherent family of probability kernel, which you can put them together and construct a measure on path space, but essentially the minimal information you need is this coherent family of kernel, which define how continuous random motion from point to point in time. And the idea of Ito was that he wanted to introduce a basic building block, a tangent to this family of probability kernels. So you see this as evolution in a probability space, and then you wanted the tangent process of this evolution, and identified it in Brownian motion in case of, okay, you can be more general and consider large class of Levy process, but essentially in the diffusion case, it's a Brownian motion, the basic object. And then you have a tool. So this is the analysis, okay? You find a basic object with which you can reconstruct all the rest of more complicated object. And then the link from the local picture to the global picture was given by a stochastic differential equation, okay? That's why Ito introduced stochastic differential equation, because they give this local description of your Markov process. And then, of course, stochastic analysis is a probabilistic version of analysis. And in analysis, you have similar players. You have you want to analyze curve, continuous curve, and then you have polynomial, which are like these local objects with which you can reconstruct more complicated curves. And then you have calculus and Taylor expansion. And then you need to have essentially this building block to construct an analysis. That is, you need to identify a parameter along which you want to consider change in a very generic way, and then a building block to build up from very small changes a global change, okay? So let me draw a first table, dictionary. So this is classical analysis, which essentially was born with Newton's idea to describe global objects, which are trajectories of planets and ellipses in particular, via polynomials, and the connection, so the link with from the local global description is given by Newton's law of motion, okay, and ODE, second order ODE. And then Ito calculus, Ito version of calculus, so the object you want to study is a Markov diffusion. You parameterize with this family of kernels. They satisfy this global property, which is the Chapman-Kolmogorov equation. So this is your global description. And then you go, you bind the local description with the local description, but the transition kernel looks locally like a Gaussian. And then this introduced like a Brownian motion, which is the simplest picture you can have for this family of Gaussians. And then you have the link, which is a stochastic differential equations. Okay, so that's stochastic analysis, classical stochastic analysis, let's say. And now I want to make a parallel and interpret stochastic quantization as a stochastic analysis of Euclidean quantum field. So instead of a Markov diffusion, your object of interest is an Euclidean quantum field. So you describe with a probability measure on a S prime over D, and here you have this family of kernels. And then the global description, so now here you have the Chapman-Kolmogorov equation, and here you have this vague description given by this Gibbs measure. This is what you would like to have. The change parameter, so now here you have a natural time, and here you have this fictitious time of stochastic quantization. And then in the local description, you say, okay, your field, you need to understand what happens when you change a bit this parameter, and what happens if you analyze a bit, if you have some familiarity with the SDE, is that you have a corresponding simple object, which is somehow an evolution in time of a Gaussian free field, which is an Oster-Uhlenbeck process, okay, which is solution of a linear equation. Exactly like here, the Brownian motion is the solution to the equation with constant coefficients, essentially, okay? So I draw the parallel. This is my first point I want to make, okay? So if you interpret Ito calculus as stochastic analysis of Markov diffusion, then I want to interpret stochastic quantization as a stochastic analysis of an Euclidean quantum field. Okay, the fact that it's a Markov process, it's not very important to me. And I don't think it's very important actually overall for the final goal. It's a case that it's a Markov diffusion, okay? Let me make this funny parallel that is somehow these are two books. So on the right, you have this book, which is essentially a compendium of what we know so far, or at least the important result in the Euclidean approach to quantum field theory. Okay, it's the book of Glim and Jaffe, which is the only book I know which can be, treat the subject in some organicity. Of course, there are many research papers, but this is the only book I know of. There are book of Dimok actually, of Better also, but it's less known. Okay, this is the most known book, and then this is the most known book which treats essentially about Brownian motion and continuous martingale in general. Okay, not even diffusion process. Okay, so you see that essentially there is something strange intellectually that is essentially Brownian motion occupies as much space as a large class of model. Okay, so my impression is that the field of stochastic analysis of quantum fields still needs a lot of pages more. Okay, I would expect like a book on quantum fields to be at least 10 times the book of Brownian motion. Okay, if you think about the complexity of the two objects. Okay, so there are a lot of pages to be written there. And let me discuss a bit varieties of stochastic quantization, just to make the point that Markov property is not very important. So it happens that Parisi-Wu parabolic stochastic quantization is a Markov process, as we already see. There is also another kind of Markov process you can introduce. So that's not surely the only one. You can introduce as canonical stochastic quantization, which somehow is an evolution in phase space, which when you write it down looks essentially like a wave equation, a stochastic wave equation. This has nothing to do with Minkowski space. Okay, it's a wave equation for the Euclidean space with an additional time, which is fictitious, still fictitious time. And that has not been very much explored. And it's not clear to me if it's really useful from the point of view of stochastic quantization, but it's something you have to keep in mind if you want to study the subject in its broad generality. Okay, you can do also canonical stochastic quantization. And then there is, for example, elliptic stochastic quantization, which was introduced by Parisi and Surlas. That's, for me, very, probabilistically, it's very interesting object. Essentially, the point is you can write an elliptic stochastic differential equation. So there is no Markov process here. There is no time. You have an additional parameter, which is a two-dimensional coordinate, Z, I call. And the idea, what is the connection with the Euclidean quantum field? Essentially, the idea is that the invariant solution to this equation, when you compute for a given Z, they are a function of X, and as a function of X, they give you an Euclidean quantum field, okay? And there are some progress in the study of this elliptic equation. Even the link with the Gibbs measure, it's not so obvious to write it down. Okay, it requires some supersymmetry, which maybe has a link with the next talk in this session. And then there are two other methods, which has nothing to do essentially with equation of this kind, with stochastic partial differential equation in some sense. There is a variational method we introduced with Nikolai Barashkov recently, where the parameter, the additional parameter you analyze is a scale parameter. So this goes into the relation of renormalization group. So you decompose your field scale by scale, and you use it as a building block. And the equation which links the global to local, it's given by a stochastic optimal control problem. And this is a link with RG method. So I put also RG method, maybe not really in the classical point of view, but recently, for example, Roland Bauer-Schmidt and with Bodino used, and also Bauer-Schmidt with Hofstetter used the RG method more as a kind of stochastic analysis in the sense maybe I will describe later. But essentially the variational method is a way to interpret the RG method, and the stochastic optimal control problem has a corresponding Hamilton-Jacobi-Bellman equation associated. Okay. So somehow stochastic analysis, just to make the point, so somehow in classical ways, in more classical ways to analyze the Euclidean quantum field theory, you want to describe the effective action or the moment generating function of the theory. And while when I think about stochastic analysis, I'm thinking more, I want a way to describe the pathwise properties of these random fields, okay? So, and this is what stochastic quantization gives to you, okay? Any of these kinds I described to you essentially give this the same picture, that is, it constructs the interacting field as a function of the Gaussian free field. So you take a Gaussian free field and then you have a complicated nonlinear function which give you the interacting field. So it's not about giving a density with respect to the Gaussian free field, it's more about the push forward of the Gaussian free field with respect to a pathwise given function. And then the estimates, essentially the analysis go through estimates via PD techniques and probabilistic estimates. And what you have at the end of the day is not just a measure, you have a coupling of your measure with the Gaussian free field, okay? That's very important. That's a feature which is not obvious in other approach as far as I understand them. And really you have this coupling, okay? So at the end of the day, you don't get just the measure, so you don't construct the Gaussian, the interacting field. You just have this coupling, and this coupling come with very nice property which allow you to compare the interacting field with the Gaussian free field. So even in cases where the measure it's not absolutely continuous. So in general, you don't expect that the interacting field is absolutely continuous with respect to the Gaussian free field, but this coupling still it's quite good and useful for analyze, okay? So that's the advantage to me of stochastic quantization. And it's really what I mean by stochastic analysis, okay? Like in classical stochastic analysis, you go back, you want to analyze a diffusion, but you essentially go back to the Brownian motion, and then you transport result of Brownian motion to the diffusion. Here you can transport result from the Gaussian free field to the diffusion. And yeah, so I have maybe a few minutes, but that's fine. So now let me maybe give you an idea what kind of results you can get by this coupling. Okay, let me take, for example, as an example, the 543 measure. If you know it, otherwise it's just the measure which you would obtain if you take a fourth order polynomial in the formulas I gave you above, and you consider three-dimensional space. You can look at the detailed construction in this paper we wrote with Martina, which appeared in Communication Mathematical Physics recently. And for example, what kind of result you can obtain? Well, for example, you can study the 4-point function of the theory by using this coupling, okay? You write the interacting field as the Gaussian field plus correction term. The correction term is non-Gaussian, but you know many things about it, in particular regularity properties, which allow you to, for example, if you want to prove non-Gaussianity of the measure, then you decompose in this way. Of course, the 4-point function of the Gaussian field vanish, but essentially by using the information you get from the estimate, from the PD estimate, you are able to prove that many terms are zero, and some of the terms, which, sorry, not zero, but a very small, a high energy when you look at very high incoming momenta, for example, and then you can compute perturbatively at high incoming momenta the first term. So it's a non-perturbative computation, but become perturbative at high momenta. Okay, you have estimates which allow you to ignore all the perturbative higher order perturbative contributions, and then you prove that it's non-zero, okay, in this way. And more importantly, for example, you can construct, you can analyze very easily, though this take a page or two, is not very complicated, to analyze the renormalized cube, okay? So you take the interacting field, you smooth out, and then you construct a nonlinear expression like the cube, local nonlinear expression, and then you're able to prove that the limit exists, okay? This is a kind of operator product expansion, if you want, result. And you can write the cube as the cube of the Gaussian free field, the plus correction term for which you have a precise expression. And as a result, you are able to prove very nice thing, in my opinion, like that you can define the cube of the Gaussian of the fully interacting 543 field, not as a random variable. So it's not a random variable with respect to the measure, but it's a distribution. So it can be tested with smooth random variable, but it cannot, for example, is not in L2, is not a usual random variable. Okay, you have to think rigorously. It's a linear functional on cylindrical functions of your field, and then you can prove Dyson-Schwinger equations, for example. Okay, which is a description of the measure. Okay, it's if you need to give a rigorous description of 543, that's the only one I can give. Okay, so it's the measure which satisfies this integration by parts formula, where the cube appears. Okay, so it's important to construct the cube because you need this integration by parts formula. And you see that in the cube, in this formula, the cube is always computed integrated with respect to a nice cylindrical function f. Okay, but essentially this formula allows you to generate all the correlation function for the theory, for example. Okay, so let me maybe give you. Okay, let me skip the outlook, mostly just pointing out that maybe you have heard by the talk of Ilya Cheverev that we made, that there are advances in the analysis of the small scale problem and the renormalization for Yang-Mills fields. Chandra, Guntaram, and Weber have a nice result about phase transition using these ideas of stochastic quantization. There are still problems. We don't know essentially how to prove uniqueness using stochastic quantization in the full space and maybe in high temperature or low temperature or phase transition. Okay, phase transition, there are some initial results, as I told you. What are open problems? Well, open problems, if you look at Yang-Mills, for example, while there are progress in the renormalization of Yang-Mills, it's not clear how to study the full space and the long time behavior of the dynamics. So this I termed coercivity. So somehow you have to send the local solution to global one, or anyway, you have to find a way to globalize your solution. And then what about fermionic fields? And there are some recent progress by Beverio, Borazzi, De Vecchi, and myself. We introduced a stochastic analysis suitable for fermionic fields. And then many problems. For example, how to study decay correlation in the spirit of stochastic analysis. So I think we have some initial result with Hofmanova and Rana, postdoc in Bielefeld. Many interesting questions I have. For example, which I don't know the answer. Okay, does Dyson-Schwinger equation determine the measure? In the sense that if I give you a measure which satisfies this equation, in some sense, can you tell me that it's unique or not? And that's to me very interesting question, even how so to pose it. And yeah, so other question I would not discuss at the moment. So that's end for me. Thank you a lot.
Hey, thanks for the interesting talk. Questions? Any questions from the online audience, Hendrik?
No, the online audience didn't have any questions.
Okay. Yes, Christophe, please.
Can you just comment on the problem about Borel summability that you mentioned at the end?
Yeah, because so, I mean, to me, of course, we are very far from even reproducing most of the result of the classical approach. Let's say the one in the group of Grimm and Jaffe with the phase space expansion. But for example, one thing you can prove is Borel summability. That is when the coupling, that is the correlation. So you can construct correlation function non-perturbatively, then you want to prove that if you now expand this correlation function as a function of the coupling constant, which I didn't emphasize, then you want to prove that somehow this series is Borel summable. Okay, so this would link perturbation theory with somehow this non-constructive method. And one idea, and you see, you can play this game to say, okay, this result, you know it's true. With other method, can you prove it in the spirit of stochastic quantization? Okay, so at this moment, I'm in this phase that is, I cannot prove new result yet. Actually, it's something, it's proven, but somehow we try to understand better the method, okay? How you can prove Borel summability, exploiting these equations, how you can prove decay of correlation, exploiting the equation without going back to more classical method. And this is for me, a test bed to understand better this method and what are the potentialities. So that's, so the proof exists, but I want a method we use only the equation to prove it, okay? I don't want to use like cluster expansion or any other kind of expansion, okay?
Okay. If there are no more questions, let's thank Massimo Gubinelli again.
Yeah, thank you for having me.
And our last speaker for the session is Tyler Helmuth. Tyler, are you online?
I'm here, yes. Can you hear me?
Yes, there you are. So, okay, good. You're sharing your screen. Okay, so our last speaker is Tyler Helmuth from Durham, and you can all read the title. So, thanks for coming, sort of, and, and you can start.
Okay, so good to be here or there, so to speak. And thanks very much for the invitation to give a talk. So as you can see, what I want to tell you about is random forests, magic formulas, and hyperbolic symmetries. And sort of I'm going to focus on this and just say a little bit about the other two parts because there's only so much time. And this is all based on two joint papers, one with Roland Bauer-Schmidt, Nick Crawford, and Andrew Swan from a couple of years ago, and one very recent one with Roland Bauer-Schmidt and Nick Crawford. So one benefit is I think Nick is there, so you can ask him questions afterwards if need be. Okay, and the talk is sort of going to be focusing on a very specific problem that I think is pretty interesting from a probabilistic point of view, and trying to point out, open questions, and sort of that this is connected to a lot of probabilistic objects that have been studied a lot over the past decades, but seems to have some pretty interesting behaviors. Okay, so let me show you a few pictures first. These are pictures, not simulations. I just drew them, so they're not super accurate or anything. So this is a picture of bond percolation, which we heard about from Tom yesterday. So I just want to take a slightly maybe perverse view of bond percolation, depending on what you think. I just want to think of it as being a measure on edge subsets that says that every edge subset has probability proportional to some beta to the size of the edge set. Okay, so it's sort of the statistical mechanics way of looking at it. And I, moreover, sort of want to think of each of these things as being an individual lattice animal. So I'm looking at some gas of lattice animals. So we know a huge amount about percolation in many settings, in part because you don't have to think of it using this language. You can instead think about it where you have an independent random variable on every bond. And that's, certainly the canonical way to think about percolation. So this talk is going to be about something else that superficially looks pretty similar until you squint at the picture and notice that every component that you look at here contains no cycle. So every component is a lattice tree. So what I'm looking at, the probability of any configuration is beta to the number of edges, but then I have a constraint that the edge set forms a forest. So I call this the arboreal gas. Well, I don't call it that. I think Solur and Jakobsen first gave it that name. So here's the two pictures side by side, and what's sort of one possible motivation for introducing this constraint? Well, one motivation comes a long time ago from Lubensky and Isaacson in the late 70s, and they discussed these two models as being different models for a gelation transition for systems of polymers in some solution. So in that point of view, what you think is that each of these connected components represents a polymer of some type. Each vertex is sort of one basic unit forming up a polymer. And depending on how those polymers or how those molecules interacted, it changes the topology of the possible polymers. So percolation has no constraint on the topology of the polymers. They can contain cycles and do what they want. While here, for the arboreal gas, there's some constraint that the topology has to be a tree for every individual polymer. So percolation we know a lot about, and if you want, you can interpret the phase transition for percolation as being a gelation transition. So you go from having only small polymers floating around in your solution to them meshing up and forming one giant polymer and then some little ones off to the side. So that's the formation of a gel, at least in 2 and higher dimensions. And you could wonder, well, what happens if you have this topological constraint? So that's mostly what I'm going to talk about. To sort of set things up, though, let me remind you of some basic facts about bond percolation, or summarize one fact, I guess, about bond percolation. So if we work on ZD, at least 2 dimensions, then there is some critical percolation parameter between 0 and 1. So that if we look away from criticality, so P not equal to PC, then the probability that 2 vertices 0 and x are connected, well, it looks like theta of P squared plus some exponentially decaying term. And the important thing is that this is 0 if P is less than PC. So that's the subcritical phase, and it's strictly positive if P is bigger than PC. So the probability you're connected, at least away from criticality, is either purely decaying exponentially, or there's a positive probability due to the gel plus some exponentially decaying probability. And this is not a particularly easy thing to prove, particularly the decay in the supercritical regime, and it relies on things like the Grimmett-Marström theorem. So this is an infinite volume theorem about percolation. So just a remark, this 2-term formulation contains in it sort of a duality that's quite interesting. It says that you're subcritical off the giant component. So if I ask what's the probability 2 vertices are connected, but I insist they're not in the giant, then it decays exponentially both in the subcritical and supercritical regime. And this is not actually specific to ZD. This is known for many other settings. For example, for the Erdős-Rényi random graph, which is just percolation on the complete graph, there's also this duality. And there are similar results much more generally, I think, including some very recent ones, say by Contreras, Martineau, and Tassion. So on much more general graphs. Okay, so that's the fact I want to remind you about bond percolation. And now I want to tell you about what happens for the arboreal gas. And before I do that, let me sort of emphasize that there's a bit of a difficulty when you want to study the arboreal gas, which is that percolation, because of its representation as independent random variables, you can trivially think about this picture, or almost trivially, as being an infinite volume. The model makes sense right away. While the arboreal gas is actually, bond percolation conditioned to have no cycles in it. So that's a very singular conditioning. So you have to work in finite volume. And there's not a lot of monotonicity properties known. Well, basically none. So basically we're stuck working in finite volume and making uniform statements. Otherwise you'd have to make subsequential statements, but I'd prefer to just work uniformly in finite volume. Okay, so what happens for the arboreal gas? Well, here are 2 theorems. So the first theorem with Roland, Nick, and Andrew is that in 2 dimensions, there is no percolation phase transition for the arboreal gas. So this conditioning, or this topological constraint on the polymer types has a profound effect, and it destroys the phase transition. And recently with Roland and Nick, we proved that on ZD, if D is at least 3, then there is a transition. So the transition survives in 3 and higher dimensions. So I'll state more precise forms of this in 1 second, but this is probably a good point to already say that, Christophe's nice talk set me up very well. This phenomena might look familiar to what he talked about. Okay, so what are the theorems slightly more precisely? Well, we prove that if you take any box inside of Z2, then no matter what beta is, there's some polynomial rate of decay for connection probabilities between 0 and x. So in particular, there's no way that the tree that the origin is in can have a positive density. Just by computing, the expected density can't be positive. So this is a finite volume statement, and we can sort of conditionally make some infinite volume statements. If you assume infinite volume limits are translation invariant, then you can really say there's no infinite component as well, but we don't know that all limits are translation invariant. So somehow this finite volume statement is a little cleaner. What about 3 and higher dimensions? In what sense is there a percolation phase transition? Well, in this case, it's very convenient for us to work on a torus. So here, n is the side length, and n you should really think of as being some large integer, power of an integer. And then the result is that if you take beta very big, so you've sort of tried to put a lot of edges into your system, or the occupied fraction of the polymer should be relatively large, then the probability that the origin is connected to a site x, well, it looks like some constant. And this constant is similar to 1 minus order 1 over beta, plus a correction term that looks like a constant over beta times 1 over x to the d minus 2, plus a lower order term. Okay, so in particular, this first term already says that you have a giant. It says that the expected size of the tree at the origin is comparable to the volume of the whole system. So let me make some remarks and point out some interesting questions that I think this leads to. So one remark is that this result I just showed, the correction was decaying polynomially, unlike for percolation. In percolation, the correction was decaying exponentially. So this phenomena has actually been observed in the arboreal gas before in a simpler setting. So in the setting of the complete graph, like the Erdős-Rényi model, Uchek and Patel showed that there's a similar phenomena in the following sense. They showed there's a phase transition for the model. They showed that at criticality on the complete graph, the biggest component size is of order n to the 2/3, which is the same size as the critical component size in the Erdős-Rényi random graph. And then they proved, I think, what is the most interesting result of their paper, which is that in the supercritical regime, there's a unique giant, so meaning a tree of size order n. But they also proved that the second biggest tree is of size n to the 2/3. So the second biggest tree in the supercritical regime is of the same scale as the critical size. And it's not just the second, it's also the third, the fourth, the fifth, and so on. So this is a similar phenomena to the result I just showed you on the torus, in the sense that it says that if you remove the giant from the supercritical regime, you look critical. So unlike for percolation, where you look subcritical, now you look critical. So here's a concrete question that I think would be interesting to answer. So, a question is, if you look on the torus, okay, maybe I don't want to say for D at least 3, but I want to know, is the second biggest of similar size or not? Okay, and I think it should be true, at least if D is at least 6, but it's not so clear for intermediate D. Okay, so that's an interesting problem, I think. Another connection to make is that if you restrict yourself to a finite graph and take beta to infinity, then the arboreal gas becomes the choice of a uniform spanning tree. And the uniform spanning tree has been studied an enormous amount in the probability literature over the years. And one of the basic phenomena that it has is that the infinite volume limits depend on the dimension you're in. So a natural question is, is the infinite volume arboreal gas geometry, like the uniform spanning tree geometry, at least when d is greater than or equal to 3. So concretely, a question is, in infinite volume, how many infinite components? And I think a natural guess is that in 3 and 4 dimensions, there'll be a unique infinite tree, and in 5 and higher, there will be infinitely many infinite trees, but that's an open question at this point. Okay, so a third remark, which is that from the point of view of percolation, I think this behavior is surprising. Instead of having a supercritical, subcritical duality, you look critical instead. And you have this absence of a phase transition in 2 dimensions. But it's actually it's not surprising at all once you take the right point of view, which is not obvious, but Caracciolo, Jacobson, Salur, Sokol, and Sportiello, in a paper that motivated us quite a lot, showed that there's a hidden continuous symmetry in this problem. And once you know there's a continuous symmetry, then the comments that Christophe, or the discussion of Christophe at the beginning of his talk, sort of explains why you might expect these phenomena, or at least some of them. So what is the continuous symmetry that they found? I'm going to describe it in a slightly different language than they used because it was useful for us. So vaguely speaking, you have a spin system where at each vertex you have a spin ux, which is some vector living in the space H02. So H02, I'll mention what it is in one moment, but the confession or celebration that I should make immediately is that the components are Grassmann variables, which is maybe exotic from the point of view of classical probability theory, but very useful for the analysis. If you like, you can sort of think about it as being similar to the ON vector models that Christophe talked about. The important thing is that it encodes connectivity. So the probability 2 vertices are connected in the arboreal gas, meaning in the same tree, is encoded by the spin-spin correlation of this spin model. So this is really saying that H02 is 0 state Potts, and the arboreal gas is the 0 random cluster model. And exactly like the Potts random cluster model correspondence, that also happens here. Okay, and in this paper of these 5 authors, they predicted both of these theorems that we've proven so far, but they made a much more exciting conjecture, I think, which is that renormalization heuristics say that the behavior of this model, the H02 model or the arboreal gas, should be like the O3 model, more or less, meaning that in particular, in 2 dimensions, correlations should decay exponentially at all temperatures. Or if you like, connection probability should always decay exponentially. So we managed to prove polynomial decay, but conjecturally we're very far from the truth, and it would be extremely interesting to know how to do this. Okay, so that's a sort of rapid introduction to the problem and some open questions. And I think it's fair to say that the way that we've studied this so far has been using tools from spin systems. It would be very interesting to see if there can be progress by more traditional probabilistic methods. What I want to do in the rest of the talk is give you some hint of what this continuous symmetry is. And I'll do that in 2 ways because different people in the audience may prefer different ways of describing it. So one thing I'll do is I'll quickly describe H02 for those who like that. And then I'll show you an explicit formula that shows you at least a shadow of the continuous symmetry as I sort of make some comments on how we prove these results in 2 and 3 dimensions. Okay, so H02. To describe H02, it's good to remember a simpler space, H2, the hyperbolic plane. So there's something called the hyperboloid model of the hyperbolic plane, and it goes as follows. You take a vector in R3, U, and I'll call its coordinates psi, eta, and z. And you look at this Lorentzian inner product. So if I have a vector u at a site x and a vector u at a site y, the inner product is 8xi minus zz. And the hyperboloid model of the hyperbolic plane is that h2 can be realized as looking at the equation u dot u equals -1, where z is positive. And if you take the metric you get from the ambient space, this becomes the hyperbolic plane. Okay, that's h2. h02 is exactly the same, but now psi and eta are anti-commuting variables, meaning they're generators of a Grassmann algebra. And you define a spin model exactly as you would expect, using the right analog of Haar measure, replacing integration with Grassmann integration. And the symmetries are the symmetries of the things that preserve this form. And the utility of those symmetries is that they give you integration by parts formulas or word identities that exactly relate correlation functions to one another. And that's a very powerful tool. Okay. So for those of you who don't like Grassmann algebras, or don't like them yet, here's another way to see the continuous symmetry. And it's the magic formula from the title. So this is going to be a formula for the probability two sites are connected in the arboreal gas. And it's a formula that's true for any finite connected graph of distinct vertices. So to state the formula, which will be somewhat complicated, I need a Laplacian, a weighted Laplacian on my graph. So it's just some edge weights beta x, y at every edge, and then the Laplacian you'd expect. And I also sort of need a tilted version of those edge weights, where if I have a field taking values in the reals, I tilt beta by exponential tx plus ty. Okay, once I do that, you can prove the following formula. The probability that 0 and x are connected in the arboreal gas is exactly this somewhat complicated integral, where you're integrating over a field at each vertex, except for 0. So the field at 0 is pinned to be 0. Every other vertex, you have this weight e to the -3t dt. So that's where the 0 appears. The x appears here in a factor e to the tx, and then you have some sort of statistical mechanical density. So there's a cosh term saying that the t's stay close together along nearest neighbors. And then there's the complicated term, which is the determinant of this tilted beta Laplacian raised to the power 3/2. And the 0 here just means delete a row in a column, so that this is non-zero. Okay, so this formula is not so easy to parse immediately. It's kind of remarkable that there is a formula. Here's some other comments. The continuous symmetry is here. So up to the pinning at 0, you can absorb this factor into the determinant, and then the integrand is a function of the gradient of t. So now you have a translation symmetry of the integrand, and that's a shadow of the bigger continuous symmetry that exists. As you might guess from Christophe's talk, you prove there's no phase transition by a Mermin-Wagner argument. And specifically, how do you do it? Well, you use this formula, you use an argument due to Christophe Sabot, and you use a word identity. And that's all I'll say about it, I think. The thing maybe that I'll remark on slightly more is that why does a Mermin-Wagner argument already exist for expressions that look sort of like this? Well, it's because if you change the 3's to 1's, so there's a 3 here and a 3 here, if you change those to 1's, then this term is essentially the mixing measure for the vertex reinforced jump process or edge reinforced random walk. So if you've never heard of those before, there are sort of models of self-interacting random walks that have received quite a bit of attention since the late 80s when they were introduced by Diaconis, or at least the edge reinforced random walk. And they have the property that if you rescale their local times correctly, you can write down a density for them. And that was called the magic formula a long time ago for the edge reinforced random walk. And that's why we call this the magic formula. And sort of Sabot and Thérèse are the first people who noticed some connection to hyperbolic symmetry. And it turns out that this works more generally. So it's important to obtain this formula that you have this hyperbolic interpretation of the spin system. In particular, you have to make use of horospherical coordinates, whose relevance for this problem was sort of, I think, first appeared in this paper of Spencer and Zernbauer. Okay, so I think we're at the end of when the session is supposed to end. So let me just say 1 minute about 3 dimensions. So here, we need to prove that there's a broken continuous symmetry for a system with continuous symmetry, because breaking the continuous symmetry corresponds to the emergence of a giant component. And as Christophe discussed plenty, we don't have great tools for that. He described a new one for a related problem, and I don't know if it works here. It'd be interesting to see. We do something else. So we use the renormalization group in the way that it was set up and used by Bridges and Slade and Bauerschmidt and Palmberg and Wallace in recent years. So we use that in combination with ward identities and an approach to finite volume due to Brezin and Zinchestan. So I should say we're helped a lot here by the fact that it's a fermionic theory. That makes renormalization group much easier. So for the experts, here's briefly sort of how it goes. But I mean, very briefly, we want beta to be very big. And the first thing we do is we introduce some external parameter h not equal to 0. This is the ghost of percolation theory. And then we want to take h to 0. Okay, and then we work in the h02 representation, and we just solve this constraint defining h02 and expand in coordinates, if you like. And that looks a lot like the phi-4 model, but there's a quartic interaction. Fortunately, it's irrelevant in the renormalization group sense. Okay, you do an RG analysis. This involves inserting some new couplings and making sure they scale correctly and so on. It's not a short story. And then to go back to the arboreal gas, what you need to show is that if you take the mass of the Gaussian that you're perturbing to 0, you need to know that h goes to 0 as well. So you recover results for the arboreal gas itself. And the way that we can do that is by making use of ward identities. So sort of you use the continuous symmetries that apply relations between correlation functions to pull things back to the world you want to be in. Okay, so I don't think that says much to anyone but the experts, but that's all the time I have, so thanks.
Okay, thanks for a very interesting talk, Tyler. Questions? Yes, Christophe.
Hi, Tyler. I was wondering, when you are in large dimensions, as you said, you expect a kind of infinite volume random forest with several components. So I was just confused with the statement that the probability in finite volume that distant points are connected is lower bounded from below by something that does not degenerate. Does this mean you consider kind of free boundary conditions, or how does it?
Right, so the result I stated was only for the torus. And different boundary conditions would be interesting, but we don't know how to prove that at the moment because of the technique. And of course, what should the disconnection into multiple components will be the same story as for the uniform spanning tree. The connections are just going too far away, so you lose them in the local limit.
I see. So you don't see those within the torus yet.
Right, on the torus, because it's a finite thing, you still see them.
Okay, great. Thanks.
Yes, please.
The exponent in your polynomial or upper bound in dimension 2, does it get better as beta goes to 0? And if you get some sufficiently fast polynomial decay, do you think there is any chance of bootstrapping that through renormalization to the conjectured exponential bound?
I don't recall off the top of my head how it behaves. It's not a very good exponent. you can sort of imagine that if you could prove that it had integrable decay, that would be enough, but I don't see how to make that work.
Okay, if there are no more questions, maybe I'll ask one. What happens if you take more than 2 fermions per site? Are there any equivalent results?
So then Nick proved that there's no transition in 2 dimensions. The interpretation is a bit trickier. So there is a probabilistic interpretation, but it's kind of hard to describe the probabilistic model, actually, at least at present. So and you have a magic formula as well. So there's lots of things that seem to be there, but the story is incomplete right now.
I see. And did I want to ask something else? Okay, I forgot. Okay, any questions from the online audience? Hendrik?
No questions from online.
Okay, so I don't know about everybody else in the audience, but I enjoyed all 3 sessions enormously, so I want to thank everyone, and next time.